Uh, Good afternoon.
Good afternoon, sir.
Yeah, so welcome to this live session on 4 November 2025. Okay, so today we are going to discuss this root locus technique. So what you can expect from this topic is, so what exactly the root locus technique is, okay, what exactly or what is the necessity of this root locus technique is, and what are the different steps to draw the root locus and an example. Okay, so we are not going to discuss many problems. Instead, we'll try to understand why do we need to go for drawing a root locus plot, then important steps. Then we'll see one example. If you understand this picture, okay, so you can solve more problems. Okay, so that is the aim for this live session. So in coming Friday's session, we'll discuss more problems. Okay, so in the previous live session, we have seen this RH criterion. Okay, so where RH criterion, so what we are doing basically over there is we form something called as the RH array. After that, we will check the first column. Okay, then we will see the sign changes. Okay, then we will decide whether the system is stable or unstable. Okay, sometimes we will also find the range of values for the gains. Correct. So in previous live session, we have seen all these steps, right? So if you observe there, okay, so there we are not interested in a particular value of gain. Okay, instead we can be able to decide analytically what is whether the system is stable or not for given the closed loop transfer function. Okay, so suppose if you have a lower order systems like first order and second order, it is easy to check the uh, stability, whether the system is stable or not, or it is easy to find. Okay, so easy to design controllers for such kind of systems. Whereas if you have higher order systems, okay, so the question is, how can you design controllers for systems of higher order? Okay, so this root locus technique is going to help us to specifically design or to alter or modify the roots of the system. Okay, so basically this is a graphical technique. Okay, so which you can use to determine the migration of the closed loop poles. Okay, so as you change the controller gain, okay, k, so the poles location is going to change. So this root locus technique is something, if you can see the all the path of roots locus when you change the parameter. So you'll see that through an example clearly. Okay, so look at this block diagram where we have open loop system. Open loop transfer function is g of s, and controller is k of s. Some function of uh, k of s is controller transfer function in terms of yes. Okay, so we have this feedback system. Okay, so we know how to calculate this closed loop transfer function, that is nothing but kg of s kg divided by 1 plus kg, that we know already. Okay, let us say here the k of s controller is proportional gain. It means that we'll have only k. Okay, so substitute k here. So kg by 1 plus kg, where g is g of s. Okay, so what is characteristic equation? Characteristic equation is this, you made it to equal to 0. Okay, so if you find the roots of this one, so they are called as the closed loop poles. Okay, so now, so what you do basically, if you choose one value for k, let's say k is equal to 1, you will get one set of roots. If you choose k is equal to -1, you'll get another set of roots. So let us say what you do is basically we wanted to select that particular k, okay, which satisfies your required speed, accuracy, and stability of the system. Okay, that means you wanted to have particular rise time, okay, or you wanted to have your steady state error is this much only. Okay, so that will be satisfied, let's say particular k only. Okay, so what you do is by simply varying this k, okay, you can place your poles in a particular region of interest. For example, you can see here, so this is the region of interest where you wanted to place your poles. Okay, by placing the poles in this region, you will satisfy your requirements like a particular uh, rise time, particular settling time, particular steady state error. Okay, so the main aim of this controller design is to meet these objectives or to place your poles in a particular region of interest, something like this. Okay, so that in that way you wanted to choose your k. This is the main aim of any controller design. So for example, see here in this aircraft example, in aircraft, okay, so something called as static stability. Static stability means, so you'll have two main locations. One is called as the center of gravity, another is called as the aerodynamic center. Okay, so basically center of gravity, that is deals with the center of mass. Okay, something related. And aerodynamic center, it deals with the center of all movements. Okay, so we can say that this is CG is center of gravity, AC is aerodynamic center. Okay, we can say that the aircraft is stable, okay, when CG is in front of AC. This case CG should be ahead of AC, that is stable. So we can say aircraft is unstable when CG is behind AC. So here CG is ahead of AC, CG is behind AC. Okay, so this is the meaning of static stability. So what we do basically, we move the aircraft. Okay, so in aircraft there is something called as the elevator here. So it is kind of flapping, so which can move up and down, which can move up and down. So this is called as the elevator. If you move up, so the aircraft will go down. If you move down, the aircraft will go up. The nose will pitching. Okay, the nose will either pitch or pitching up or pitching down. Is this clear? This example?
Yes, sir.
Yeah. So just by moving elevator, okay, so you can make the aircraft nose pitch up or pitch down. So the pitching we will represent with Q. The elevator angle will move with some angle which represents with delta E. Okay. So you can by moving the elevator, you can pitch up or pitch down, so that this is the location we can change, so either to the head of AC or behind the AC, so that you can change the stability behavior of the system. Okay, so let's see here. These are the dynamic equations for an aircraft. We don't need to understand here, just to uh, see these are the two equations. Okay, here alpha is the angle of attack, Q as I said pitch rate, and delta is the elevator deflection. So these are important. When you change the delta E, the Q is going to change. That is what we need here. It means delta E is the input here, Q is the output here. Okay, so you can see delta E is the input, Q is the output. Okay, so now to those equations, if you apply the Laplace transform, okay, and simplify these equations, you'll get this transfer function. We'll get this transfer function. So transfer function is Q of S by delta E of S, which is this expression. Okay, so where Q of S is the output, delta of S is the input. Okay, it means, so if you just change this input delta E, there is a change in Q you can expect. Okay, so now you are dealing with this. So So let's take some values for all these coefficients when you substitute into this equation. Okay, so let's say you got this. Okay, so values are also not important. We are not interested in the dynamics of the system. Okay, but we are interested in the this example. Okay, so now let us say in this configuration, so aircraft is unstable. Aircraft is unstable. Here you should have delta of E of S. Okay, so here open loop system is stable. Why? Because you see the poles location. This is, what are the poles? P is equal to minus 2.97, that is one pole. Second pole is 0.575. So this pole is existing in the RHS side. Yes or no?
Yes, sir.
So system is unstable. Okay, so one pole is on left side, one pole is on right side. Okay, now so when the system is unstable already, it means that, so this configuration. Okay, so if you change your elevator, this particular elevator, it will make system more unstable. It will make a system more unstable if you change it in the opposite direction. Okay, so that we don't want to do. So let's see. So now this is the, we wanted to design a proportional controller autopilot. So basically controller means autopilot only here. So we wanted to design a proportional controller. That's why we took this K, amplifier K. So these are the aircraft dynamics. So Q of S is the output, delta E is the input. Okay, that means this transfer function, this is nothing but your G of S, that will be represented here. Okay, so the actuator means you wanted to move your elevator, which is the deflection plate. So using this servo motor. Okay, so assuming that its transfer function is 1. Okay, then we have this proportional controller. So then we have this feedback which measures, which is a sensor which measures the pitch rate, that also having 1. H is 1. Okay, so now, so this is the transfer function we have. This is K. Okay, now this is the reference pitch and this is the actual pitch. So here you wanted to apply your delta E. Okay, so if you properly choose your K, that will make your system stable. Basically this is unstable system. Okay, so now what you are doing is you have this system here, H is 1. Okay, so what is this Q of S by Q C of S, because that is like Y of S by R of S, correct?
Yes, sir.
Yes, right. So you find this if this is G of S, what we do, G by 1 plus GH. Okay, so G is nothing but this. Once you find that, you will have both the numerator as well as denominator. Okay, so closed loop transfer function or characteristic polynomial is nothing but what? You make that denominator equal to 0. Okay, so this is the equation. Okay, is this clear? Any queries as of now?
No, sir.
So this is characteristic polynomial. Okay, so now we are applying this RH criteria. So we have S square S and S power 0. S square S and S power 0. So S square coefficient is 1. S coefficient is this, that we took here. Then S power 0 coefficient we took here. Okay, so you know how to calculate this term. That term is nothing but, so this one multiplied this, 1 multiplied 0 divided by this term. So you get what? This term only here. Okay, so now you see, you observe the column 1 elements. Column 1 elements is 1 is already greater than 0. Okay, then 2.93 you are taking greater than 0, the other term also greater than 0. Okay, the first one is giving K is less than 0.106. Second one is giving K is less than minus 0.47. So what is the intersection? Intersection will be this. Okay, so it means that, so the system is stable if you take K less than minus 0.047. Is this clear?
Yes, sir.
Any value. So, or you can take in the orders of 1, minus 1, minus 1, minus 2, etc. That will make your system stable. Okay, so previously without controller, when you see here, so one pole is existing on the right side, one is on the left side. So when you add proportional controller and apply the RH criteria, right? It is giving us a range for the value of K. So whatever the value you take in the orders of -1, -2, etc., that will make the system stable. Okay, so this we know already. Okay, so here the issue is that, so this example is very simple one. This example is very simple. Whereas very simple in this sense, the order of this equation is only 2. Order of this equation is only 2. Okay. But whereas if the order is very high, okay, sometimes in the previous class we also have seen when you take PD controller, PI controller, instead of K, you'll have two terms, KP and KI. Yes or no?
Yes, sir.
Right? So you need to find some region. Okay, so you need to find some region. Let's say this is Ki, this is Kp. So you have to find some region, okay, where both are satisfying this stability property. Correct? So that will be that will be the case when the systems are of higher order also. Okay. So the question is, if you are having systems of higher order, it's not very easy to obtain the K value, and also the when you have multiple gains, it will be difficult. Okay. So in such cases, so we go for this root locus technique. So what this technique will give us is, it will give us the approximate locus of the roots, right? Means approximate the path of the roots, how they will vary if you keep on varying the gain. Suppose for in this example, okay, so you got this region. Okay, when you substitute k is equal to -1, you will get one set of poles, roots. When you substitute k is equal to -2, you will get another set of roots. When you substitute k is equal to -3, you will get another set of roots. Okay, so basically what this root locus will do, give you is, it will give you a path. It will give you a path like this. So this will be k is equal to -1, -2, -3. Is this clear? So starting
Yes,
from either from 0 to infinity or 0 to -infinity, it will give you a kind of path where you can easily see that how the roots are diverging, how the roots are varying, in which direction the roots are going as you vary the k. Okay, so let us consider this example here. Okay, so let's say we have this open loop system. Okay, open loop transfer function. So let's say we are including the proportional controller. So that means we have including this k. Okay, so this is closed loop transfer function for unity feedback, let's say. So now you got this d of s. Okay, so let us consider that d of s. Okay, and take this Routh array. Okay, so you'll have s cube, s square, s power 1, s power 0. So 1, 8, 32, 1. So 1, 8, 32, 1, 32k. Okay. So you're finding this term as 8 multiplied by 32 minus k multiplied 1 divided by 8. Okay. That will give you this one. This is 0. This will be again this term multiplied k, 8 multiplied 0 divided by this term, that will give you k. Is this clear? Okay, so
yes, sir.
for stability, what is the condition here? Already 1 and 8, they are already greater than 0, and these two terms, one term is greater than k is greater than 0, second term is 32 minus k by 8 greater than 0. It means it will give you k is less than 256. K is less than 256. So now if you see here, one value is k is greater than 0, another is k is less than 256. It means that for stability, what is the condition? Your k must be 0 less than k is less than 256. Clear?
Yes, sir.
Yeah. So now you can get you can take any value of k between this range. It will make your system stable. Okay. Suppose if you substitute k is equal to 0 in this term, what will happen? Can you tell me? For k is equal to 0, for k is equal to 0, so this d of s, so d of s would be what? S cube plus 8s square plus 32s, correct? So this I can write s multiplied by s square plus 8s plus 32. So what are the roots? So P1 is equal to 0, 1 root. What are the other roots? P2 and P3, can you tell me? What are the other roots? We will get minus b plus or minus b square. Okay. So you will get this root. So you'll get complex conjugate. Let us calculate them. What are the roots? Minus b. Minus 8 plus or minus root over b square. Okay, 64 minus 4 into 32 into 1 divided by 2 into 1. Correct? So here if you could see, this is negative. Correct? Inside term
Yes,
is negative. So obviously that will be zeta. Okay. Here you can see 2 and 4. It means that it is something like minus 4 plus or minus j. Correct? So that
yeah,
means
it's around 4J.
my, yeah, minus 4 plus or minus something. Okay. Now you see at k is equal to 0, this is the value. Correct? And this one also. These are the three values. Am I correct?
Yes, sir.
Yeah. So now you could see at k is equal to 256. When you substitute k is equal to 256, you will get poles exactly on the z omega axis. You'll get poles exactly on the z omega axis. Okay, two
Okay.
poles. Two poles you'll get on the z omega axis here. Okay, one pole you'll get somewhere here. Is this clear?
Yes, sir.
So in between, if you take any value, let's say if you take some k is equal to 100, okay, you will get one pole here, another pole here, another pole maybe here. Okay, so if you keep on taking the k value as 1, okay, so the poles will be like this. K value as 2, the pole will be like this. Okay, it means that as you increase the k value between 0 to 256, the pole location changes like this. Exactly at 256, this pole, it will be here. This pole, it will be here. Okay. If you take any value k is greater than 256, they will go to the RHS plane, right hand side plane. Is that clear?
Okay. Yes, sir.
And this pole at k is equal to 0, it moves like this. Okay. Now you see these blue lines. This is one line. This is another line. This is another line. Okay. So what are these lines? When these are the poles paths, when you keep on increasing the k value from 0 to infinity. Clear?
Yes, sir.
This is called as the root locus. This is called as root locus plot. Is this clear? Any query?
How do we account for less than 0, sir?
Yeah, less than 0 also we can draw. So basically what we learn here is, so positive values, but we can also do the same thing for k less k minus 1, minus 2, etc. minus infinity also. Okay. That is also a special case. Usually what happened, practical cases, the gains will be positive. So,
Oh,
I
okay,
mean,
sir.
the application case. So that's why we almost discuss with k varying from 0 to infinity, but we cannot avoid that negative values case also. But still, we will get some problems from minus 1 minus k is equal to 0 to minus infinity also.
Okay.
Okay, so this is the main essence of the root locus. When you vary this gain from 0 to infinity, so how your poles are moving, okay, at what point they are crossing the z omega axis, right? They are going to infinity. What is there in the infinity? These are the important questions. Clear?
Okay, sir.
So do they meet someone in the infinity? So that is an interesting question. Okay. So now here what we have is system is very simple one, third order system. Okay. But when you have the system of order very high, okay, let's say order of 10th, okay, it will be very tough to find these poles location because we cannot apply this formula. Exactly, correct?
Yes, sir.
So that's why this root locus technique will give us some systematic steps to draw this root locus plot. So once we have the root locus plot, we can easily see here where the poles are starting and which direction they are moving. Once you know this once you know this picture, you can do anything in the system. Like, so here you can see the poles are crossing this omega at 256. Okay, so when you are dealing with the real systems, what you do, you will not go up to 256 because at that point you are crossing into the unstable region. Okay, so you will limit yourself in the maybe k is equal to 200 or k is equal to 100. Clear?
Okay, sir.
Yeah. So now we are going to see the steps of the root locus. Okay. So first what we will do is these are the two things. We can discuss the steps. Okay. So and their proofs. Then we can go for the example. Okay. The other way is directly we will see the example. From the example, you will understand what are the steps. Then we can come back and see what exactly the steps are telling us. Okay, what we do here is I'll give some basic one or two steps. Then we'll go to the example and see how using those steps we'll draw the root locus. Then you can come back and see the proofs of those steps. Okay, so first step here is he is the person, so Ivan, so he articulated this root locus technique. Okay, first what we do is we put our the transfer function into this events form. Okay, so what this events form is, we will write like this: g1 of s divided by 1 plus k g2 of s. Okay, where k is the parameter which we wanted to vary. Okay, and we wanted to plot the roots of this equation, the denominator 1 plus k, this one plus k g2 of s. So any transfer function we will first put it into this events from. Then we wanted to plot the roots of this for different values of k, which varies from 0 to infinity. That is our main aim. But we have to keep our transfer function into this form. So for example, here you can see the basic proportional control system. So if you find the closed loop transfer function, what is the closed loop transfer function here? This one. If you see here, that looks like exactly same. So k g1 of s divided by 1 plus k g2 of s, right? This form exactly. So k is not there here. Okay. So it means that this is already in the events form. Okay. First we
Yes,
have
sir.
to put it into this form. Now let us say if you take the PD controller, okay, PD control, again you find the closed loop transfer function y of s by r of s. How do you find that? G of s multiplied k1 plus k2 s by, so 1 plus g of s k1 plus k2s multiplied 1, h is 1. Okay, in this, suppose if you fix k1, if you fix k1, so this is the we have closed loop transfer function. If you, we can write this one as in this way. Okay, so by taking this numerator. Okay, so now here you could see this is g1 of s and this is g2 of s. Okay, now you can see this looks like the events from, if you fix k1. If you fix k1, then what we do is we wanted to check the roots of this denominator. Okay, so denominator, this will be your z2 of s. Okay, so same thing. Next also you can see this integral controller. It means that simply k we are replacing with k by s. Here also k by s. Okay, now in this, so this total is the g1 of s, and here this is g2 of s. Okay, so we have to be very careful. Next, you can see this PI controller. Okay, for different controllers, what you need to do is you have to put that in the events form, first step. Okay, so you should know exactly what is your G1 of S and G2 of S. So that is first step. Okay, is there any doubt in this?
No, sir.
Yeah. Uh, okay. Okay, so next we'll review some basics, then we'll get into the directly the example. Okay, so first you can see here we have this complex plane. So we have this complex plane. Okay, in the complex plane, any point z shall be represented with x plus iy or zy. Okay, where we will which has the magnitude of r and the angle is theta. So we can write like r e power j theta. Okay, in the same way, e power j theta is nothing but cos theta plus j sin theta. Okay, where we know that r is the magnitude root over x square plus y square. So we know already tan theta, cos theta, and sin theta. It means that any complex number in this, okay, in this complex plane, we can write its, this is the rectangular form, this is the polar form. Okay, either in the rectangular form or polar form. Okay, any complex number z. Now let's say we have this zk. Zk is a complex number. Okay, then let's say we have another number, another complex number s. Okay, so this is one number, this is another number. Okay, now we wanted to find this quantity, which is difference between s and z. Okay, so how can you find? So you can see here, so this quantity, okay, this quantity is, this is the angle theta zk. Okay, then you have this s, you have this zk. Okay, so this is the magnitude. Okay, sorry, yeah, this is the magnitude of this vector. Okay, and this is the angle. So you can write any vector, you can represent as rzk e power theta zk. Clear? Any query here?
No,
You
sir.
can represent, yeah, you can represent like this. Okay, any vector, any vector in the complex plane. Now, so first step is, after writing the transfer function in the events form, so the first step is angle criterion. Again, consider this proportional control system. So in the proportional control system, this is our closed loop transfer function. Okay, so what we wanted to do is we will write this denominator in the events form. So this is what we are interested in, 1 plus k of s g of s. 1 plus k g of s is the transfer function of the plant. Okay, which has g of s as both the numerator as well as the denominator. So we can write that g of s, okay, by finding their poles and zeros. Okay, what are the zeros? Zeros are nothing but roots of n of s equal to 0. What are the poles? Roots of d of s equal to 0. Okay, here z1, z2, zm are the zeros. Okay, p1, p2, pn are the poles. Okay, so where this g of s is the open loop transfer function. Okay, so GC of S is the closed loop transfer function. Okay, is there any doubt? Here Z1, Z2, Zm, they are the open loop pole, open loop zeros. P1, P2, Pn are the open loop poles. Okay, any
Okay.
queries? Because
No, sir.
root locus always we start with the open loop poles and open loop zeros. Okay, by starting with open loop poles and open loop zeros, we will decide the stability of the closed loop system. Okay, now you start with this because you wanted to find the roots of this equation. We shall make that one equal to 0. So the second part as it is. Now you see this part we have just derived. What is this part is r e power j theta. Am I correct? Okay, so this one. Is this clear?
Yes, sir.
Yeah, so similarly for pole also we can write. So for every pole and every zero is represented in this way. Okay, now you can take all these the magnitudes out for poles and zeros. Okay, so now all these angles exponential is same, so you can add all those angles in the denominator also. You can add all those angles. So then you can take this as one number. Okay, so here e power summation of the zeros angles, e power summation of the poles angles. So what you can do is summation of zeros angles minus summation of the poles angles. Okay, you can write it as r e power j theta again, where r is nothing but, so this term, theta is nothing but this term. Okay, now you can see interesting here. So we have r and theta, summation of all the zeros angles minus summation of all the poles angles. So you know already this e power j theta is cos theta plus j sin theta. So why I am explaining this thing is we will be getting into the conclusion in a systematic way. Okay. Now you see here in the left side we have minus 1 by k. Right side what do we have? R e power j theta. So this minus 1 by k, we can write 1 by k, the minus 1. We can write in this way. E power j pi plus L 2 pi in the using the trigonometric relation. Okay. So now you can see here, if you expand this, if you expand this term, okay, that will be like cos pi plus 2l pi plus j sin plus 2l pi, this term. Okay, because e power theta is cos theta plus j sin theta. Okay, so that gives simply minus 1 by k. It means that this minus 1 by k you can replace with this term. That's what I wanted to say for different values of L. Okay, so now you can see we have these two relations. Okay, so this theta we got as pi plus 2l pi. Okay, now you are going to define the angle criterion. So the angle criterion says, okay, so the angle criterion says, okay, if there is a point, if there is a point, yes, if you wanted to say that that point is on the root locus for some value of k, okay, if and only if sum of all the angles that it makes with the poles minus sum of all the angles that it makes with the zeros is 180. That means sum of all the angles that S, point S makes with the zeros minus sum of all the angles that it makes with the poles, that has to be equivalent to this expression. Is this clear?
Yes, sir.
Yeah. So then we can say that this point S is on the root locus. We'll see in the example clearly so that you'll understand it better. Okay. So this is the angle criterion. Okay. So what do we do generally? So you take the S point. Okay. So you have this, let's say you have this ZK point. I said yes. Okay. This is ZK. Okay. What we do? So we find this S minus ZK. Okay. So you will measure this angle, as I said previously, you will measure this angle. Okay, then so you will find this expression. Then it has to be equivalent to 180-degree. If it is 180-degree, we will say that S is on the root locus. Okay, so that we will see in a couple of minutes with the example. Okay, now here you see this is the example pictorially. So we took two cases. Now how many poles this image has? So one pole, second pole, okay, and zeros is 1 0, second 0, correct? Two zeros and two poles, am I correct?
Uh,
Yeah,
yes, sir.
two poles and two zeros. Now your doubt is, this is the point I am considering, that is as yes. Now your doubt is this S is existing on the root locus. As I said, what is the root locus? Those poles variation curves, correct? So to check whether this S is on the root locus or not, okay, what we do? So from yes, from this pole you draw a line. Okay, you find this angle. Is this clear?
Yes, sir.
From this pole also you draw a line, find this angle. Okay, from this 0 also draw a line, find this angle. From this 0 also draw this line, find this angle. You see what is the common thing here? All the angles are clockwise, anti-clockwise. You see
Oh,
that? All the angles are
anti-clock.
anti-clockwise and they are with reference to this horizontal line.
Okay, sir.
This horizontal line. You see that? So they are all reference to this horizontal line. Okay. Now what you do? You got two angles with the poles, two angles with the zeros, correct? So substitute here. Summation of zeros angles, summation of poles angles. Okay, take the difference. If it is equal to 180 degrees or equal to this one, pi plus 2l pi, then you can say that the point S is on the root locus. Clear?
Yes, sir.
So this is another variation where instead of S is on the real axis, we have taken S is on the somewhere in the complex plane. Again, here also same thing. So draw these four lines. Okay, so find these angles. Find these angles. Now you have two angles with the zeros, two angles with the poles. Again, apply this equation and check whether it is equivalent to 180 degrees or not. Okay, this is called as the angle criterion. Angle criterion, what it says, it will give us the flexibility to check a particular point, yes, whether it is on the root locus or not. So here is the previous is the proof. Okay, so I'll give this file later, you can check that. Okay,
Okay.
so there are some advantages also. Now you see here, this one angle, this one angle. What is the key point here? If you see these two angles, if the poles are complex conjugate, by seeing this angle and this angle, what you can say? You will get 360 if you add them. Yes or no?
Yes, sir.
Yeah, so that is one advantage. It means that if you just calculate one angle, the other one you will get by subtracting from the 360.
Okay,
So
sir.
these are simple rules. Okay. So and important point here is this one. Okay. So the root locus always lies. The root locus always lies left of the odd number of poles and zeros on the real axis. It means that you wanted to check, this is the real axis, this is imaginary axis. Okay, you wanted to check, so whether this real axis, okay, is which part of the real axis, which part of the real axis is in the root locus. What you need to do is you have to check from the right side. You have to check from the right side and see how many poles are there in the left. Root locus always existing on the left of odd number of poles and zeros. Okay, so you wanted to check real axis part which is in the root locus. This is the rule we need to follow. So we'll see in the example quickly.
Okay.
Okay. So that is one example. Second is, suppose we are saying that S is here. Okay. Okay. So now if any pole is 0 on the real axis, previously what do we have here? The poles are zeros in the complex plane. Whereas here, where are these poles and zeros? They are on the real axis. Okay.
Yes, sir.
Now
Yes, sir.
you wanted to find what is the angle of this pole with a point S. That is first question. Okay. Then second question is, what is the angle of this 0 with this S point? Okay. So can you tell me what is this? This one makes with 0 degrees. This one makes with 180 degrees. Is that clear? So let me
Yes.
put it here. So this is your S point. Okay. This is the pole. Okay. Now basically what we do is from pole, okay, draw a vector. Okay. Now you start moving it anti-clockwise. Okay. You start moving
Yes,
it anti-clockwise. Already you have this reference line. Okay. What is the angle? This is 0 only. Correct?
yes, sir.
Yeah. Other way is, let's say you have this S here, you have this pole here. Okay. Now you wanted to find what is the angle. Okay. What angle from the pole to S. Okay. Basically what you do is, you will start here. You will start with the horizontal line. Okay. You will slowly move this one like this. So how much angle it has to go to reach here?
180.
180. So is this clear? So
Yes, sir.
that means if any pole is on the, if this is your S point, if any pole are 0 on the left side, they'll make 0 degrees. If any pole are 0 on the right of this S, they'll make 180 degrees. Clear?
Yes, sir.
That's it. Okay. So now we are going with the example. So same example. Can I leave? Yeah, just give me 2 minutes.
Yes, sir.
Thank you. Yeah. Can you hear me now?
Yes, sir.
Yeah. So we are starting with this open loop transfer function. We wanted to go for proportional controller. So this is the closed loop transfer function. Now this form is already in the events form. This is G1 of S and this is G2 of S. So this part, okay, now we wanted to find the roots. Okay, so for varying this k from 0 to infinity, varying this k from 0 to infinity. So simply it means that if you vary k from 0 to infinity, you wanted to see how the poles are moving. Okay, initially they are here. So you can see. Okay, so let's consider the open loop transfer function. What is the open loop transfer function? This one. Okay, we have uh, one pole at minus 2.97, another at 0.575. So 0 at minus 1.62. Am I correct?
Yes, sir.
Yeah. So these are the three values: Z1, P1, P2. Okay. So let us say Now you can see here, I'll try here only, you will understand. Okay, so this is real part, this is imaginary part. Okay, so first P3, P3 is this. Okay, next P1, P1 is this minus 2.97. Okay, let me write it here, minus 2.97. Then Z1 is minus 1.62. Is this clear?
Yes, sir.
So these are open loop poles and zeros. Okay, this is our first step for drawing the root locus. First, we will put the open loop poles and zeros on the S plane. Okay, first step. Then second step, what we do is, as I said, this point. So what we do is, we will start from this side. Okay, so let's say we have started coming from this side till this point. Okay, how many poles we have?
0 poles.
We have one pole, correct? I mean,
Okay.
let us say, no, let us say till this point. Till this point, right side, how many we have?
1 pole.
One. Okay, it means that if you consider any of these points, if you draw this dashed line any of these point, at till that point you'll have one, correct?
Yes, sir.
So it means that you'll have, this will be on the root locus.
Okay.
Okay, now if you draw that line here, so now you see the right side.
There are 2.
uh, you see the right side, you have 2, correct?
Yes, sir.
Yeah, so it means that if you take up any point here, okay, so any point right side is 2 points, correct?
Yes, sir.
So but that has to be odd number. Okay, now so if you take up here, it will be 3, correct?
Yes, sir.
So it means that this is on the root locus. You got that point now?
Yes, sir.
To decide which segments are on the root locus, so you will come from the right side and decide it. Okay, so this part is not on the root locus. This part, only this part on the root locus, this part on the root locus. Is this clear?
Yes, sir.
Yeah, you can see this part on the root locus and this part on the root locus. Okay, so this part is not on the root locus. Okay,
Yes, sir.
yeah. So same, we can check the another example. So open loop transfer function. So this is closed loop transfer function. Again, Evans form. This is your Z1. This is your Z2. Madam came. She has no, my office is. That's why I yes. Hello. Yeah. So now for this open loop transfer function. So we have 0 here. So the open loop transfer function is like this: G of S, K of S. Clear? So that is K multiplied S plus A by S tau S plus 1. Is this clear?
Yes, sir.
This is open loop transfer function, not G of S. It has to be multiplication of both. Okay. So now in this, the 0 is minus A. The poles are 0. Okay. And this one is minus 1 by tau. Is this clear?
Yes, sir.
Yeah. Now again you see them. So this is pole. this is pole, this is 0. Okay, again you come from this side. Okay, if you take up any point in middle, any point here between this one and this one. Okay, if you see right side, you'll have only one pole, correct?
Yes, sir.
If you take up any point here, from there if you see right side, you'll have only one pole. It means that that segment is on the root locus. Okay, now if you choose, if you are here right side, you will see only two poles, that is even number. Okay,
Yes, sir.
so obviously that is not the part of this, this is not on the root locus. Okay, whereas this is on the root locus. Now you see this point, this segment will be on the root locus. Why? Because if you stay here, see right, you will see the two poles and 1 0, odd number. Okay,
Yes, sir.
yeah, so this is on the root locus, this is on the root locus. Okay,
Yes, sir.
so now for this system, okay, we have drawn only this much. Okay, this is partial, this is full. Okay, so this is partial root locus, this is full locus. What is the difference? Can you tell me?
It traces the path
So
of.
yeah, so basically the roots are starting at these three locations at k is equal to 0. Okay,
Okay, sir.
as you increase the k value, what is happening in this root and this root? They are traveling in the opposite direction. They are meeting at this point, correct? And one will go to this direction, another will go to this direction. They'll again meet here, correct?
Yes, sir.
And one goes towards this 0, another will goes towards this infinity. Am I correct?
Yes, sir.
The question is, how are we going to draw this path and this path, and how can we say that they are meeting at this point and this point? Clear?
Yes, sir.
From this is the partial. Okay, from the partial, how can I draw this full? Okay,
Yes, sir.
so that will be given by the steps of the root locus. Okay, so let me go through that. It will just take 10 minutes.
Sure, sir.
Yeah. Okay, now I'll go through the example. I'm not going to the steps how they came. So from the example itself, you can understand. Okay. So first, this is the open loop transfer function. Okay. So we are going for the P controller. So this is closed loop transfer function. Is this clear?
Yes, sir.
So in this closed loop transfer function, if you take this one, okay, 1 plus k, this term equal to 0. If you vary k from 0 to infinity, okay, for every value of k, if you take the roots, okay, and plot them and connect them, you'll get manual root locus. Yes or no?
Yes, sir.
But using root locus technique, we wanted to get that root locus using this open loop transfer function. Okay, so for PI controller, what is this? K of s is k. Okay, now sorry, this is not open loop. Open loop transfer function means, so g of s, k of s. Clear?
Yes, sir.
Yeah. So we'll start that. Okay, first what we do is, so we'll do the step 1. So we are writing into Evans form g1 of s by 1 plus k g2 of s. So first you will see what is that g2 of s. So this is the expression. This is nothing but the g of s and k of s only, which is nothing but open loop transfer function. Clear?
Yes, sir.
If you write it, you'll get that one only. Okay. So it means that this is the starting point for the root locus. That means this one. open loop transfer function only. Okay.
Yes, sir.
So first what we do is we will first find the open loop poles and zeros. What are the open loop poles? 0, 2, okay. Then -1 plus or minus 2, J2, roots of this equation. Clear?
Yes, sir.
Then open loop zeros. Z1 is -3. Okay. So now here we have n is 4. That means number of open loop poles are 4 and m is 1. Okay. So we are going to use this n and m. This is first step. Is this clear?
Yes, sir.
So first step what we are doing. So find the open loop poles and zeros. Locate them on the S plane. Okay. So where we have here 1 0. Sorry, here one pole. Yes or no? P1, P2. Then this is -1. Correct? This. Is this clear?
Yes, sir.
P3 and P4. Okay. So where we have z is this is -3. Is this clear?
Yes, sir.
Yes. So let me copy that. I'll use the same image every time. Okay. So that is first step. Any doubt in this first step?
No, sir.
Okay. Next. So we are putting that. Okay. Second. So second is we have to find the starting and ending points. Starting point, ending point. So what we get is n is equal to 4, m is equal to 1. Correct? Okay.
Yes, sir.
So what is m minus m is 4 minus 1 is equal to 3. Okay. So here what is happening is all these 4 poles, okay, and 1 0. Okay. So out of the 4 poles, one pole will go to 1 0. Is that clear?
Yes, sir.
So any one pole will go to this 0. Okay. And remaining 3 poles, they will go to infinity. Okay. So that's why we said starting and ending. Okay. They will start at these points and they will go to infinity. Is that clear?
Yes, sir.
Suppose if n is equal to 3, m is equal to 2. So n minus m is what? 3 minus 2 is 1.
1.
Okay. It means that out of 3 poles, 2 poles will go to 2 zeros, 1 pole will go to 1 0. Is that clear?
Yes, sir. 1 pole go to infinity.
Yes, yes. One pole goes to infinity. Okay. So it depends upon n and m and n minus m difference. We will say that which pole is going to 0 and which pole goes to infinity. Okay.
Yes, sir.
Number of poles and zeros. That is second step. Next, step 3 is okay. So we'll find the real axis segments in the pole. Real axis segments of the root locus that we have seen already. Okay.
Yes, sir.
Let me show you again. Okay. Now to do this, what we do again, start from here. Okay. Suppose here right side how many we have?
1.
1. Okay. So that means this is on the root locus. Correct?
Yes, sir.
Now here 2. Correct? Right side we
Yes.
have 2 poles. So this part, okay, so this part will not be on the root locus. Okay.
Yes, sir.
Okay. So I'll remove that. Okay. Next. So that is over. This is over. Next, this one. So again same, that is also same, correct? From
Yes,
this
sir.
point, yeah, this from this point to This entire part, that is same only, no? Wherever I draw that. Okay. Now this part, how many we have? Total 5. Yes or no? Including both
Uh,
poles and zeros.
no, yes, sir. Yes, sir.
So that will be, this is part of the root locus. Is this clear?
No, yes, sir.
So we come from right side and check for the odd number of poles and zeros. Okay.
Yes, sir.
Yeah. So I'll remove this. Is this clear? Any doubt?
No, sir.
Okay. So I'll use this. Okay. Okay. So that is second step 3. Next step 4. What we do is we will do 2 calculations: asymptotes and asymptotic centroid. Okay. So asymptotes is this angle. Asymptotic is this angle where alpha is what? 0, 1, 2, 3, etc. n minus m plus 1. Okay. What is n here? 4. M is 1. What is alpha is 0. What is n minus m plus 1 is 4 minus 1 plus 1. Correct?
Yes, sir.
So what is that value? What is that value is? That will be 3. Correct?
Yes, sir. So n minus m, not plus 1.
N minus m. Yeah, n minus m. Correct. Okay, so that will be 3. Correct. So we'll get n minus m plus 2, I think, at that one.
That will be n minus m minus 1.
Yeah, so we should get this one only, 0, 1, 2 only. So that will be n minus m plus 2, I think.
No,
So
minus 1.
4 minus 1 plus 2. Correct. So n minus m. Okay, let me check. So we should get
Minus
the
n minus m minus 1.
minus 1. Okay, sorry. I was wrong. So that will be n minus m minus 1. Okay, so 4 minus 1 minus 1. That will be 2. Is that clear? So alpha
Yes,
will
sir.
be maximum 2. 0, 1, 2. Clear? So what you
Yes,
do
sir.
is you will substitute here. First you will substitute alpha is equal to 0. You'll get 60. Clear? You'll substitute
Uh,
alpha is equal to 1. You'll get 180. You'll substitute alpha is equal to 2. You'll get 300. Is this clear?
yes, sir.
Next, so these are called as the asymptotic angles. Okay. Next is asymptotic centroid. This is the formula. So what we do, this is the summation of the poles, summation of the zeros by n minus m. Okay. So what are the poles we have? 0, 2, this is one pole, this is one pole. Correct.
Yes, sir.
So that is the summation of the poles. 0 is only minus 3. Correct.
Yes, sir.
So divide by n minus 3. N minus 3 means 4 minus 1. Okay, what we are getting? 1. Is this clear?
Yes, sir.
So what we do now is, this is already the image we have, correct? Okay. So what is the centroid here? We got
1.
centroid is 1. So somewhere here, correct? So
Yes,
that
sir.
is sigma. That is sigma. Okay. So next, by taking that sigma as the center, we will draw these 3 angles with respect to this x-axis.
Okay.
Okay. So what is the, with respect to this x-axis? So what is the first angle? 60.
60.
Okay. So we'll go like this. This will be 60. Am I correct?
Yes, sir.
Next is 180. This will be 180.
Yes, sir.
Okay. Next is 300.
Minus.
This will be 300. Got it?
Yes, sir.
So these are called as the asymptotes, the green ones.
Okay.
Okay. The green ones are called as the asymptotes. So I'll take this one. Is it clear? Any doubt?
No, sir.
Yeah. Now next. So next is we will do two things because we said that uh, there are two things: departure and arrival. Departure means we said that starting here is yeah, starting and ending of the root locus points. Correct? We said that we have four poles, 1 0. Correct? Out of
Yes, sir.
four poles, one pole will go to 1 0 and three poles will go to infinity. Correct?
Yes, sir.
So poles are always going. Am I correct?
Yes, sir.
And one pole is going towards a 0. It means that poles will have departure angles, zeros will have arrival angles. Okay.
Yes, sir.
So okay. So first what we do is for each pole we will find the angle of arrival. Okay. For each zero we will find the angle of for each pole we will find angle of departure. For each zero we will find angle of arrival. Is that clear?
Yes, sir.
So let's see the first one. So angle of departure. Okay, it means that a particular pole, okay, how it is departing from its initial location. Clear?
Yes, sir.
So we will use this equation. What this equation says is, so from that particular pole, how the summation of all the zeros angles, okay, then that particular pole angle and summation of all poles angles. Clear? So let me
Yes,
show
sir.
you here. Let me show you here. Now we are interested to find this P1 departure angle, that is 3 theta D1. Is that clear?
Yes, sir.
What we do is here we have total three other poles, 1 0. Correct? So from 0 we will find the angle. So how do we find the angle? We know already. From poles also we find the angle. Okay. How do we find the angle? I
No,
told you
anti-clock.
already. Yeah,
Yes.
anti-clockwise direction. Okay, so let's say if you consider this, what is the angle? Tell me. For this angle will be, you have to
300.
take, you have to take this angle. Clear?
Yes, sir. Yes, sir.
So in trigonometric, you know how to find that angle because you know this pole's location. That means
Oh,
you know this distance, you know this distance. Correct?
yes, sir.
You can find that you can find this angle, and the total angle is what? 360.
Yes, sir.
You can take the subtraction. Clear?
Yes, sir.
Okay, so I think it is clear. So that is how we can
Yes, sir.
find. Okay, so
Yes, sir.
this angle, that is this one, 180. Okay, this angle, that will be 0. Yes or no?
Yes, yes, sir.
So that is how you will find the angles. Once you have all those angles from the zeros and poles, so now you can see here we are trying to finding the departure angle.
Yes, sir.
So theta d1 for with pole 1. Okay, so we have only 1 0 and 3 poles. Okay, and this is the angle just by following this equation. Okay, so we'll
Yes,
find those angles. Theta 0 0 is making 0. So these two, this pole and this pole, they are making 360. Correct?
Yes, sir.
and this one is making 180. So if you substitute into this equation all these, so you are getting theta d1 as 0. Is this clear?
Yes, sir.
It means that theta d1 is departuring with what? Which angle? 0.
Uh, 0.
0 means what? This
On
direction.
the real, yes. Yes.
Okay, it means that that is the starting direction. In that direction, it will go.
Oh, okay.
Okay, so next, theta d2. I'm skipping that. Theta d2 is 180 degrees. Same image. Okay, theta
Yes, sir.
p2 is nothing but what? This angle. 180 is what? This one. Correct?
Yes. Yes, sir.
So that is theta d2. Next, theta d3. So that is 232.1. Okay, so that means what? 232 in this which direction? So this is horizontal. Okay, so if you start like this, 180, correct? Yes or
Yes,
no?
sir. Yes, sir.
So somewhere here in this direction it will start.
Yes, sir.
Is that clear?
Yeah.
Next, theta 4, this one. Okay, so you're getting 180. Okay, so 180
Yes.
means what? Here 180 means what? So this direction,
Yes,
correct?
sir. Yeah.
So this is the direction, theta 4. So this is theta d4. Am I clear?
Yes, sir.
Okay. Oh, sorry. This is theta arrival. Oh, theta 4 is 127. I'm sorry. So that will be 127 means this is 90. This one. You got it?
Yes, sir.
Theta d4. Okay. So this is arrival angle. So arrival angle also same thing. Okay, what we do? So you draw the vectors from all the poles to the 0. Okay.
Yes, sir.
So again you find the angles. Okay. These angles. Is that clear?
Yes, sir.
Yeah. So now, so what we got? 180 degrees we got here. Okay. So 0 is here. 180 means what? So 180 means this way.
Yes, sir.
Theta A1. Is this clear? Oh, I'm sorry. Just a minute. No. This is arrival.
Rival.
So this is arrival means, so this direction. So it
Yes,
is
sir.
arriving in 180 degree direction. Okay. This angle is 180, but the direction is towards that.
Yes.
Okay. Whereas for poles, it is away. Is this clear?
Yes, sir.
Yeah. So that is step 5. Okay. Next, step 6 and step 7 you will see later. Now you can see we'll draw the diagram. I'm not sure. Okay, let me draw this. Extend the margin. Yeah. Oh, okay. I've skipped it. Okay. So we got this sigma here, correct? So one is 60, correct? One asymptote. Another
Yes, sir.
is 30, 300, correct? Another is 180.
180.
So this is 60, this is 180, and this is 300. Okay. Now, what will happen here is, okay, so these two poles, okay, so basically these asymptotes, what they say is, what we said initially, we have n is equal to 4, m is equal to 1, correct?
Yes, sir.
Okay, so n minus m we got as 3. Okay, so out of 4 poles, one pole will go towards this 0, correct?
Yes, sir.
And 3 poles will go towards the 0 at infinity, correct?
Ah, yes.
3 poles, okay, 3 poles, and here we have 3 asymptotes. Am I correct?
Yes, sir.
So basically 3 asymptotes, they will direct these 3 poles. They'll give the direction to go towards that side. That side. Is this clear?
Yes, sir.
Yeah. So that is the importance of these asymptotes. Okay. Now you remember this image. Now you see this. These dashed lines are the asymptotes. There is one more.
Uh,
Okay. Now you see
yes,
these two poles. You see these two poles. What they are doing? So they are coming and at this point. Okay. So they are
mm,
going away. One is following the. This is 60 degree asymptote. This is 300-degree asymptote, correct?
yes, sir.
So one is going following the asymptote 60, another is following the 300-degree asymptote, correct?
Yes, sir.
Yeah, you could see this pole is following and meeting here. This pole is following and meeting here. Out of two poles, one is reaching this 0, another will go to infinity. Clear?
Yes, sir. So
Mm,
how do you determine
mm.
these two poles that
Which two poles? These
on
poles.
the left hand side?
Yeah, yeah, I told you, no. Here we got their departure angles, correct?
Yeah, we got something like 180 something.
No,
Oh,
no,
okay,
no.
okay. No, no, no,
Yeah,
no. Yeah, yeah. We
depart
got 120.
departure
Yeah,
angle is something like this.
yeah,
Departure
yeah.
angle is
Yeah.
something like this,
Yes, sir.
and
Yes, sir.
arrival angle is 180. You remember that?
Yes, sir.
And these things also you got departure angles are 180 and 0.
Yes, sir. Yes,
You see all these red points are arrivals and departures. Okay, so
yes, sir.
this is 0. This is 180. This is something like 230. This is something like 120.
Yes, sir.
So that is the starting direction. This is the starting direction.
Okay.
Ultimately, they will reach here. This will reach here. Okay,
Yes, sir.
so one will go to this, another will go to infinity.
Okay. Sir.
Now you got the picture. So
Yes.
basically what that this mean is, these cross points, all the at k is equal to 0, they'll start at these locations, all the poles. Okay, so
Yes, sir.
as you keep on increasing the k, they will move like this. At some point of k, they will uh, break here. Okay,
Okay.
so this point is called as the uh, break away. Okay, whereas this point is called as the break in.
Okay.
Clear? So this is a nice
Yes, sir.
example where you have both break away and break in.
Okay. A break
Okay,
in, how do we calculate?
that will come next examples. So how do we calculate break away? How do we calculate break in? Okay, now you
No,
see here.
break away is centroid, no, sir.
No, no, not centroid. That is also different. Luckily here
Oh,
centroid and break away look same, but that is different.
oh, okay.
Okay, sometimes the centroid may also come here. So both are different. Okay, so now you will see when k is varying from 0 to infinity, so how poles are moving. This is what actually the Locus technique is, when you are unable to find the roots of a system, which is if the system is of higher order.
Okay, sir.
Got it?
Yes,
So
sir.
I'll share these files. Just go through this and try to solve one example, the same example. You will understand. because you need to find
Mm.
all these angles and all.
Yes, yes.
Yeah, then you'll get the better idea. So maybe on Friday we'll discuss more problems and the steps also even more clearly.
Yes, sir.
Okay. Yeah.
Yes, sir.
Thanks a lot.
Thank you, sir.